Hello everyone. In the previous class, we have seen the implementation of VGG16, the architecture, how it is built, and then we did also discussed about various layers, that is pooling, max pooling, min pooling, average pooling, global average pooling. That's we discussed how the dimensionality reduction is performed via pooling. Then I also talked about dropout, batch normalization, and then in brain tumor classification code, I told about how to do pre-processing. That means we have splitted our data into training, testing, and we have made a VGG16 architecture, including the attention mechanism. And I also talked about attention mechanism. Okay. In today's lecture is going to be very much important. And why this lecture is going to be important? Because my theme is, as we want to learn more about attention mechanism in computer vision. Okay. As per the definition I told yesterday also, attention is to attend. It means to focus. And on whom we want to focus? We want to focus upon important terms. Okay, something which is important, I want to focus upon it. I want to give more priority to it. And if I will train my model with these important terms or with these important features, obviously I'm going to get good results. Okay, fine. So, in attention mechanism, I told yesterday, we do have three components. Okay, these components are Q, K, and V. I also gave you an example how these components work. Q is a query. Okay, K is a key, and V is a value. And I refer this concept like to SQL, where we give query to the database and we want to fetch result from it. Result can only be fetched if your query matches with some answer present in the database. That can be handled with the help of a key. Okay, so in your database, you will be having key value pair. Okay, key value. I'm going to forward a query and it will return me the value on the basis of key. Okay, so now How this is converted into attention, what you told now. I need to focus upon specific parts, areas, features, terms. How this is converted into attention. So what I do have from my input, let us suppose X is your input. I need to map Q, K, and V from it. That means Q, K, V will be made from input only by multiplying it with the weights, trainable weights. Okay, by multiplying it with trainable weights. That means if you are having an input X, if I am going to multiply it with W, I am going to add bias also, it's going to make me Q query. These weights are trainable. These are behaving as a parameter. Weight and the bias, these two will be trainable in nature. Similarly, I will be having x dot wk plus bk is equal to, this will be the key, and x dot wv plus bv is equal to value. This is how you have to make the equation. Okay. So you are having an input and you have to project this input in form of Q, K, and V. Understand what I am trying to say. You have to project. Understand the terms what I am saying. Project X in terms of Q, K, and V. I am having X as an input. I need to find what is important in this input. You are available with this. Now, in order to find what is good in the available, that is why I am dividing my input, I am projecting it in the form of three components Q, K, and V. And I am taking some weights, some trainable weights. Okay, it may like, fine, you are saying that multiply x by zero point 0.2, multiply x by zero point 0.5, multiply x by zero point 0.1. So like these are certainly the weights which you have taken. This represents query, this represents key, and this represents value. These weights are dynamic in nature, they will be changing. Right now I just written here during training, during training it will change, they will be dynamic in nature. Okay, so a kind of logic which has been used here is you have to project your input in three components QKV. For that you require weights and the bias. Somewhere it's just only written x dot wq is equal to q. Somewhere they are not adding the bias, that's okay. However, I have also added the bias here to complete the equation. And it's just a reminder for you. Reminder. In machine learning, y equal to mx plus c, though it seems like, sir, very easy equation, sir. We have learned this equation. We have seen in linear, like no, linear algebra in 11th standard in school, y equal to mx plus c. You can see how these equations are looking. Can you match this format? So never underestimate this equation. This equation is like very worthy in especially in neural network. Okay, and you can see this is my input, this is my weight, this is my bias. So mx plus c, and this is my q, this is my k, this is my v. Now what you have to do after having q, k, and v? I told that you can perform a dot product. Okay, that means q dot k ka transpose. You have to perform dot product. Then you have to scale this dot product. This is called as scaled dot product. We have to perform the scaling, and then you have to take the max. This is an activation function. That is what you have to do. Here, square root of d is dimension of key of key. Let us suppose dk. That's a dimension of key. Okay, so let me write here dk. Okay, then take the softmax will give you probability values. So probability lies between 0 to 1. You know it. And then whatever be the result you are going to get from here, you have to perform the dot product of it. Let us suppose I got let me rewrite this thing. Softmax q dot k car transpose square root of dk dot v. This will be your output. Okay, there is one more thing mentioned. Weight is also been considered, wo, in order to project this answer. This will be the final output. Okay, here is what attention mechanism called. It's used in your large language models, this phenomena. It got famous from there. However, attention is not new, but it got famous from there. And if you will ask me, sir, we are having image data, sir, we are having image as an input, sir. So, are you converting image into Q, K, V? That's what, sir, you are going to do. Yes, of course, I am going to do this thing only. I am going to create Q, K, V from your input image only. Now, that's what I am having. So, I can write it here. This is wq, weight of q. This is key and this is v. Again you will be having a question, sir, ये जो query है, this query, तो query image में क्या होगी sir? What will be the query in an image, sir? Can you please tell me? तो query image में होगी कोई specific region. Query in an image will be a specific region. Okay, I need to find whether this specific region should be attended, and how much attention this require. I am querying. So query in image will be a specific region in an image. You do have an image, and we make a matrix of an image. Let us suppose this particular value we call as a pixel. Okay, and let me consider that this is my specific region. I will be querying for that. And key and value, what the key and the value will be? Key will be spatial locations. Key will be locations. So out of this image you took a specific region, and rest all will be your spatial location. Okay, and value will be the vectors, feature vectors for spatial locations. This is a location, location, location. These are the spatial locations. We are having vector representation of that. That will be the value, because it's a value, na? So that will be a vector. So query is some specific location. Key will be spatial location. Spatial means width into height. That is called a spatial. Okay, so I will be querying. I will be taking a specific region. I will be querying to my entire image that represents a spatial location, and I am going to get the value from it by applying this mechanism which I taught just now. By applying this mechanism, this is how it goes in image. Okay, let me share my entire screen. And right now we are in a very important phase of learning attention mechanism. You have to listen carefully. Okay, first of all, let me have some simple definitions, some statements like, what are attention mechanism? They help models like neural network to focus on the important parts of an image or piece of data. Okay, that's what we are doing. Okay, sir, we are already applying, sir, convolution, sir. We are having an image, sir. We do apply convolution on it, sir. Convolution, sir, we know, sir, that it is a dot product of f and g, sir. F is the matrix of image, sir. G is the kernel, sir. And sir, we do the dot product, sir, and we get a feature map. That is a matrix, sir. And then, sir, this feature map, sir, we pass through the, sir, pooling operation, sir, which gives us another matrix, sir, which is a pooled matrix, sir. And that's what we have learned in this is the fourth day of my workshop. And this thing, sir, we have learned. We are already extracting the features from the image. Then, sir, now you said attend, add, attend, attention. So how it's going to help, sir? It did help me. This workshop I just been executing because of this attention only. Okay, why? Just check the example. When you look at a photo of a dog in park, your attention focus on the dog, not the entire background. So feature extraction, we try to do that thing only, that kindly extract the features of the dog. Okay, just extract the feature. I should be able to see an object in an image. Now, dog, okay, obviously it's an object in an image. There are pixels with which it is made up of. If I can attend those pixels, if I can attend those pixels using attention mechanism, the model will be focusing on the most important parts in the image, and we can make a decision. We can make a quick decision. I hope this makes a sense. I am not focusing upon what is the background. No, I am just focused upon the object which is present in the image. Okay, and the concepts which are used in attention mechanism is the weighted sum, soft attention, and hard attention. See, weighted sum is that's what we use in general. The one which I have shown you, now that's weighted only. Okay, that's weighted sum only. And I also tell you what is the formula for softmax activation function. The formula for softmax activation is e ki power xi upon summation of e ki power xi, where xi is attention score. Okay, it is attention score. And how you got this score? You got this score by q dot k car transpose divided by square root of dk. This is attention score. When you perform the dot product and when you divided this by the square, this is attention score. And you have to give this attention score to the e power. Okay, and take the summation of all the attention scores. This will give you the probability. Okay, and then you have to multiply this probability with V. Okay, finally you have to perform its dot product with weight WO to get the final output. Okay, and weighted sum, you know that, for example, we are having the four terms. So I will be taking all the sum of the four terms divided by four. That is the weighted sum. Okay, so we do take the weighted average, weighted sum. This is the average. Okay, so this is how we do take. Here it's mentioned take the weighted sum. That means model look for the different parts on the image, gives a weight. We give the weight to different parts. Understand? Understand how attention is being applicable. You are having an image. You are projecting image into three components. You are assigning weight to these components. Okay, and then you are calculating what is q according to this weight multiply by I dot wq. So check the statement what they have written. Model looks at the different parts in the image, gives each part a weight. Every part in the image you are going to give a weight. This is your image. Okay, let's make about like grid of pixels. So weight like this. Okay, let's say we are giving a weight to them. Currently I'm having three parts. I divided into three, so I gave the weight to them, QKV. Soft attention, the model focus upon multiple parts of the image at the same time. Here continuous weights are given. The weights are continuous. Model focus upon multiple parts. In hard attention, model focus only on one part of the image, not all the parts, only one part at a time. So it's like it can be, I hope it's discrete or binary in nature. Because when I'm focusing on one part at a time, rest will be zero. This is hard attention and this is soft attention. Soft attention is continuous in nature. Weights are continuous in nature. And we do take the weighted sum in general. That's what the phenomena we follow. And there are different types of attention mechanism, different types of attention. That is spatial attention. That means you focus upon different regions in the image. Okay, important. I do focus upon different regions in the image. Then comes the channel attention. Okay, again important. I focus upon different channels. You know, na channel. RGB. I taught three channel. One channel is grayscale, and when you add the kernels, the channel goes on increases. So here we are focusing upon the channel. Channel comprises of color, texture in an image, etc. And spatial resolution comprises of pixels and patches. So we will be dividing image into pixels or the patches, and we will assign weight to them. And obviously, we are going to apply the attention mechanism. Formula will remain the same. That will be the formula. Q dot k का transpose divided by square root of dk. वो बताऊंगा अभी. Okay, fine. So channel attention, self attention. That means it captures the relationship or similarities between the different parts of an input. In an image, I want to find the similarity between the different parts. Okay, that means if this is your image, okay, how this part is related to this part, how this part is related to this part. So, like this. So, capture the relationship of similarity between different parts of an input. Okay, and these are like this term is related to the text. Okay, long term dependencies and all these things. So, vision transformer has been one of the algorithm used in your computer vision only. They apply self attention mechanism on the entire image. They apply self attention. How one part of an image is related to another part of the image. That is what VIT do. We are having temporal attention also, useful tasks and involving sequential data. Like for videos, we apply temporal attention. Okay, allowing model to focus upon important frames, etc. Okay, we are having branch attention also that involves creating multiple branches within the network. Okay, so they also follow texture, color, shape in an image, and then they combine to get the final decision. So, what we are going to do? We are going to assign the different parts. We are going to divide the image either the way you are going to create a multiple branch within a network and focus upon the different aspects of the data by performing branching, by creating branching. We do have global attention also. Consider the input sequence or data to compute attention scores. Okay. Local attention also. Focus upon the local neighborhood around each position of the pixel. Local. That means not the entire. We are just focusing upon some part of a data. This is local attention. Okay, not the entire one, just a local, specific. Apply attention on this, not on the entire data. Okay, we are having hierarchical attention also. Applies attention at multiple levels of abstraction. Hierarchy, you very well know, na? This is hierarchy. Okay, so we can perform attention here also in this ways. And memory based attention also utilizes external memory structures to store and retrieve the information on the basis of the attention. Okay, again, I told you this thing. Attention mechanism queries external memory during the processing and retrieves the facts or content. That's what I told now. I give a query to the database. From database, I am getting the result. So that's memory based attention mechanism. Multi head, again, star. This is what I have used in my algorithms. Multi head attention. See, multi head, that means not a single attention. We are using multiple attentions. They all are working in parallel. That is why we call it as multi head attention. Okay, and head, what is head? It captures different types of relationship in the input. Okay, different relationship from the input. Okay, or attend different parts of the input, allowing the model to gain rich information. Okay, and obviously in my architecture, I have used multi-head attention. That's what I'm telling. I took 8 heads. I will show the architecture of VGG16. That means I took 8 attention mechanism in parallel. One, 2, 3, 4, 5, 6, 7, 8. And I'm going to give input to them. Okay, I'm going to give input to them. They will attend them, and then the results will be concatenated. Whatever be the result I'm going to get from them, I will concatenate them. That is called as multi-head attention. We are going to see this thing. The architecture which I have used for VGG16, I will just tell about that. We see the code for this also implementation and the maths. Already I'm focusing upon that thing only. So implementing attention mechanism in computer vision, you require input. How you are going to get the input? Images are passed through convolution layer. Features are extracted. Feature maps are built. From that only, you can create query. You can create key value pair. I already told you. Query is specific region. Listen to this. Query is a specific region or the target. I need to see dog in an image. So that is your specific region. Key value pair, these are the spatial locations of an image, the entire image. Spatial locations of the entire image. Okay, that's what I called width into height. And once you got Q, once you got K and V, you very well know what to do. Okay, I will calculate the similarity. Similarity is the dot product. Then I will perform the normalization. Okay, I will do the scaled dot product and then I will perform the normalization using shortmass function. That is also been there. And then obviously I'm going to get the context vector, the result, final result, by computing the weighted sum of the feature vectors. Okay, just take the sum of all. Okay, this vector, this result shows, emphasize the important. I want important regions only in the image. Convolution is extracting the features. Convolution is getting the information from the image. But in that particular information, which is important information, that's what I need to attend. Okay, got it. Yes, any query. I guess there is some question put up. To research paper, I want to cross attention. Is it related to the multiple input? Yes, sir. You can use cross attention also. Okay, you can apply cross attention. No worries. All right, fine. Ultimately, what you are available with? You are available with the image as a data if you are working on images. Okay. So if you are working on images, yes. Now you can perform cross attention here to here and here to here. You are available with the data like in form of tokens. This is your data in form of tokens. So how this token is related to this, how this token is related to cross attention. You can do that, sir. No worries. All right, got it. There are many ways. Additive attention. Huh? There are many types of attention, sir. There are many types of attention. Differential attention. I have used differential attention also in my the projects. Okay, fine. So you have to use in your projects. You have to use these things into your research. You can go ahead with that. That's why I just kept this workshop. Okay. So here now let me talk more important things. As I told that we do follow attention mechanism to focus on the most important parts in the input, whether they are spatial regions in an image, in a channel, in a feature map. Okay, whether it is in width into height, whether it is present in the channel, you can use it according to the spatial or the channel, according to the attention mechanism which you are using. So that's the reason I'm using multi-head. I'm not specific whether spatial, whether channel. No, use multi-head. That means all this multiple attentions will come under multi-head. So one query came to me, sir. I want to use cross attention. One query came, sir. Additive attention. अरे भाई multi head ही लगा दो खत्म करो यार खेल. Apply multi head. That means mostly will cover. Okay, in terms of image, I'm saying you can have self attention also. तो अलग अलग कहाँ लगाओगे यार? Why you are going separately? Just use multi head, तो उसमें self भी आ जाएगा. Self will come, spatial will come, channel will come. Okay, global will come, local will come. सब आ जाएंगे सब ये निपटाओ एक साथ. Okay, so multi head attention works well for the images. That's why in my algorithm I got 90% plus plus accuracies on pre-trained architectures which are not been built for the latest images also. Okay, I taught you VGG16. VGG16 is for ImageNet. Got it? ImageNet is doesn't mean that you are having a brain tumor images, na. Neither brain tumor, neither breast cancer. No. But how I got good score on VGG16? What is the reason? Because we made this algorithm like we added some components in this algorithm which helping us in detection. Okay, so multiple perspectives. Each attention head captures different relationship between the image patches. Some can attend on local features, some can attend on global features, some can attend on self attention, some can perform cross attention, some can perform additive attention, some can perform this, some can perform that. That is why I use multi head. Don't be specific, sir. मेरे को तो additive ही चाहिए, sir. Rich representation. Combining multiple attention head allows the model to create richer representation. Handling long term dependencies, this is something related to like text. वो text वाला फंडा है. Long term dependencies का मतलब ये होता है, okay, we are having two types of dependency, long term and the short term. If I do write a paragraph, so any word which is present here and any word which is present here, how they are related to each other, that's called as long term dependency. Anyways, we can also apply here in our case. So like it's saying that such long term dependencies will be performed in critical tasks like object detection, object classification, segmentation, all these things. How a pixel present here and how a pixel present here are related to each other. Okay, so that's attention. Okay, and let me show you the code which I worked in brain tumor. Okay, brain tumor classification. I use VGG16. Okay, and in VGG16, you can see here, um, I added multi-head attention. Okay, fine. Let's see. VGG16. Here it is VGG16. I took it from the TensorFlow Keras, and all these layers I already explained. Here you can see multi-head attention. Okay, after downloading the weights from VGG16, its layers I made false. No need to train the layers of EGG16. I just get the weights from it. And then you have to reshape, because VGG16 is going to give you 77512. You have to reshape it. And reshape, you have to multiply height and the width. That means 7 into 7, 49. So the result here will be 49 comma 512. That will be the reshape. Okay, so this is spatial dimension 7 7, width and the height. You have to perform reshape of it. 7 into 7, 49. So your answer here will be 49 comma 512. Then you have to give this input 49 into 512 into attention mechanism. This is your attention, multi-head attention. I am taking 8 heads here. And the key dimension, okay, the dimension of the key, I am taking channel, number of channel, that means 512. Okay, that means na wo dk, under root of dk. I hope you remember this thing na form, just I taught. So the key dimension I am taking, it has 512. This is your multi-head attention, one line. Okay, now see, sir, please tell us the maths, sir. You have shown the code, sir. Please tell us the maths, how this is working on VGG16, sir. Okay, so let me tell you the maths also. Okay, let's get started with a fresh page. See, you are having an image. You performed VGG 16 over it. Actually, you perform VGG 13, not 16, क्योंकि ये भी उसको 16 13 plus 3 था ना. So that 3 was the dense layers. वो training था, तो अपन ने तो सिर्फ convolution and pooling we did used. So let us suppose VGG 13 you have applied. And after applying VGG 13, you got the result as 7, 7, 512. That's what you got after applying VGG 13. Okay, got it. Fine. And then, yes, sir.
Sir, I have one request. Can you share the link from where the data sets has been taken?
Uh-huh.
That's one thing, sir. Sir, and also the some rough approximate block diagram of the entire architecture, sir.
Sir, that I
Input
have.
till the classification,
Sir,
something like
sir,
that.
I have explained the entire architecture in the
Oh,
previous lecture, sir. All are
okay, sir.
available. All are
We'll go
available,
through.
sir.
Yes, sir.
Okay,
I'll
sir.
go through, sir.
Sir, you can go through. All right,
Sorry,
fine.
sir.
Yeah, oh, it's okay, sir. So, we are having an image and we applied VGG 13, like 16, but let's take 13 here. Convolution we applied, and this is what we got. Then this 7 into 7, I need to multiply and make it as 49, and this is what you are getting 49, 512. Now, this is your spatial dimension. This is your spatial. That means you are having 49 rows and 512 columns. That's what you are having. Okay, 49 cross 512, that's what you are having. Okay, got it. Now you have to find Q, K, and V. Things are now very much simple for you if you are very much attentive and listening to me properly. Your image is 49 512. है ना? That's what the spatial dimension is. You have to make Q, K, V from this image only. Okay, got it. So you have to take WQ, WK, WV from it. Okay, see, this is an internal process. The statement which I have included in the architecture, multi-head attention. You did not have to do this thing manually. वो internally सब हो रहा है. लेकिन what is happening? ये मैं बता रहा हूँ आपको. What is happening? I'm teaching that. Okay, so 49 512. You have to make Q. As I already told that the key dimension, the dimension of key, you can see in the code, I did mention that the dimension of key is equal to the number of channels, and right now I'm having 512 channels available to me, so the key dimension is 512. Okay, got it. So that is dk is equal to 512. Okay, I need to make, no, I need to make q. Q can only be made if I can multiply weight with I. That is the dot product with I. Then only it will be made. So what will be WQ? What will be the dimension of WQ? See, I is, okay, let me put it here. This is the dimension of WQ. I'm not writing anything. And here the dimension is 49 512. That's what I'm writing. So what will be the dimension of WQ? Or some places it's been written like this, that don't write WQ dot I. Some places you might be seeing write I dot WQ. Right, like this. Input should be considered first. Okay, so input is 49 512. What is this WQ? In order to perform the multiplication, matrix multiplication, this thing and this thing should have to be equal. So this should be 512. It's clear. This should have to be 512 only. Because if this are equal, then only I can multiply the matrix. So let us suppose for simplicity, I am taking this one also 512. Let it be. So WQ, this matrix is of 512, 512. This is my input 49, 512. Okay, and I will be doing the dot product. What values will be present here? What values will be present here? They are all randomly assigned. Randomly assigned. I'm not assigning anything. They are randomly assigned. These are weights. So neural network में weights are randomly assigned. आप नहीं करते हो, ठीक है? So I am having the image values, image matrix. These are randomly assigned, and there will be the dot product. So I'm going to get the value of q. Similarly, I will be getting the value of k. Similarly, I'm going to get the value of p. That's what I'm going to get. Okay, got it. And now, after getting all these values of q, k, and v, what has been there for you? 49 512. This is your spatial, no? This is your spatial dimension. Okay, so as I told, I am having 512 features. I am having 512 features here, and this is 1 2 3 dot 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 up to 49. That means I am having 49 tokens here. I am having 49 tokens here. This is a token. This is a token which is having 512 features. I got a token. Okay, this I'm relating with the text. In text, we do have tokens. If you write a sentence, my name is Nirmal. So this is a token, this is a token, this is a token, this is a token. Similarly, here also, I am having 49 tokens here. Okay, got it. Now, sir, you are having 49 tokens. So let us say T1, T2, T3 up to T49. 49 tokens. And sir, how you are going to apply now the mechanism? You have created Q, K, V. Okay, so if let us suppose token 1, let us consider T1 and T2. Let us consider two tokens initially. I am considering two tokens. And I am taking this as a query. Okay, so let me write like this Qt1. Qt1. I will be performing dot product with K T2. Obviously, I need to perform the transpose of it. अभी तक you are writing ना q dot k का transpose divided by square root of dk. That's what you are writing ना. Obviously, now I am taking two tokens t1 and t2. Sir, can you further simplify? Huh? Yes. You can write them like this. You can write them like this. T1, T2 dot T49. T1, T2 dot T49. Okay. Something like this you can write. And I am just performing T1 with T2. I need to find what is the attention score. So this 49 is made up of 7 cross 7. Okay, that means width and the height, that particular square, that particular pixel, you considered one pixel which is having a value of 512 as a feature. भाई अंदर का खेल है बहुत बड़ा, समझ जाओ. You are having अब अच्छा, I'm very like going uh, मेरा जो फ्लो है दैट्स वेरी नॉर्मल, आराम से समझा रहा हूँ. ओके, सो 7749. Okay, and you are having these 49 tokens. So one token you are having this 512 feature. Okay, and then you have to perform this thing. Let's consider two token T1 and T2. So if I am considering this as a query, this will be my key. So Qt1 dot k T2 का ट्रांसपोज Qt1 dot k T2 का ट्रांसपोज divided by under root of dk. What is the dimension of key? 512. So just put 512 का root here and just take short mass activation function outside and then perform the dot product dot v t1, value of t1, and then whatever be the result you are going to get, multiply it with wo. Wait, output, ये भी कुछ randomly assign होगा. This will be the final output which you are going to get. Okay, तो wo भी learned weight होगा. This all, ये जितने भी है ना, ये this all, ये आपने मेंशन करा WQ, WK, WV, ये सब लर्नड वेट्स हैं. लर्निंग ड्यूरिंग ट्रेनिंग ना, देयर वैल्यूज विल चेंज, इट विल बी डायनामिक इन नेचर. तो इनकी लर्निंग होगी, ये पैरामीटर्स हैं. इन मशीन लर्निंग, डीप लर्निंग, पैरामीटर्स की ही ट्रेनिंग होती है. तो ये लर्नड वेट्स हैं, दीज आर द लर्नड वेट्स, एंड दिस इज हाउ यू आर गोइंग टू गेट द आंसर. So in my VGG 16, this is the mechanism is applied. This mechanism applied. And again, listen, I haven't used only one head. I have used multi-head. So I will be having H1, H2, H3 up to H8. These heads I am having. Every head is performing a attention mechanism of different type. Someone is doing spatial, someone is doing channel, someone is doing local, someone is doing global, and ultimately, and what kind attention that's QKV, QKV. So this is my 49 512. I will be supplying this 49 512 to each and every head. That's what I will be doing. ले भाई पकड़ तो, और यहां पर होगा क्यू के वी, ये निकाला जाएगा. दैट्स व्हाट वी आर गोइंग टू टेक, क्यू के वी, क्यू के वी, क्यू के वी. That's what the mechanism is going to do. And whatever be the results I am going to get from here, whatever be the output I am going to get, I am going to concatenate. Add करो सबको, concatenate the results. That is why at one of the place it has been mentioned the advantage. Okay, here it is. Multiple perspectives. Each attention head captures different relationship, and on the basis of that we are concatenating. आपने अच्छा ये अच्छा काम किया, okay fine, you did this thing good, okay you did this thing good, you did this thing good, okay you all have done something good, let me combine the result to get overall good. This is what multi-head attention do in image. Okay, now few things which has been in my mind. We have taken a pre-trained model. Okay, that is VGG. The entire convolution operation has been performed. After that, we have applied multi-head. That means all convolution pooling, convolution pooling, everything has been done. Then I have added multi-head attention. Now अब क्या है कि मेरा तो दिमाग थोड़ा सा खुरापाती है, or okay, let me say in English that my brain, it's like I something which I achieve now, I never get satisfied. My working pattern is something different. And I thought that ki can we have convolution multi head attention, then convolution multi head attention, can then convolution multi head attention. Can we have something, okay, convolution pooling then multi-head attention, then convolution pooling multi-head attention. Bhai, you guys are here for some research, for some development, you are looking forward some innovative architectures. Okay sir, whatever architecture you have shown, you got the result, but we want something extra, sir. Can we try such kind of phenomena? Yeah, you can try, you can try this thing. लेकिन भाई अब कुछ देर इज एन इशू. यहां पर जो आएगा ना, मेमोरी का इश्यू आएगा. द इश्यू इज ऑफ मेमोरी. ओके, आफ्टर परफॉर्मिंग कन्वोल्यूशन योर इमेज साइज इज रिड्यूस्ड. ओके, इमेज साइज इज रिड्यूस्ड, फाइन. देन यू आर अप्लाइंग मल्टी हेड ओवर दैट. ठीक है, तो ये कॉम्प्लेक्सिटी क्रिएट करेगा. फिर देन अगेन कन्वोल्यूशन, फिर मल्टी हेड लगा रहे हो आप. ये सब कॉम्प्लेक्सिटी क्रिएट कर रहे हैं. मैंने अप्लाई कर लिया है, मैं इसलिए बता रहा हूं. जो मेरे वॉट एवर केम इन टू माई माइंड, आई डिड दैट. और ट्रेनिंग तो स्कोर अच्छा हुआ, इन वैलिडेशन वो फेल हो गया. वो 50% से इंक्रीज नहीं करा. वो ट्रेनिंग स्कोर वॉज गोइंग, थोड़ा बढ़ गया. वो 50 to 60 to 70 to 80 इट रेस, बट वो वैलिडेशन पर 50% से ज्यादा नहीं हुआ. तो माय सजेशन इज, अच्छा ये तो मेरे दिमाग में आया है, दिस केम इनटू माय माइंड. और भी एक्सपेरिमेंटल वी कैन डू, वी कैन ट्राई फॉर दैट, मोर एक्सपेरिमेंट्स, फाइन. बट आई गिव यू कि ऐसा मैंने किया था, आई डिड दैट. इसमें आई हैवंट एडेड एनी गॉसियन noise I haven't added something like koi batch normalization I think I did, dense वगैरह I did, but score was not something good. The most important thing was जो computation है, because if you are been a part of research or the PhD you have to show that part कि complexity कितना था आपके algorithm का. Okay, you have to show in your research कि I have run my algorithm on this machine on this resources and this is this much time it took. तो यदि यहाँ आप करोगे ना, अटेंशन बार बार लगाओगे ना, तो वो, तो दैट्स द रीजन व्हेन यू कन्वर्टेड योर इमेज इनटू दिस साइज. ओके, यहाँ छोटा हो गया. अब और रेलेवेंट फीचर हमने खींच लिए, वी एक्सट्रैक्टेड द रेलेवेंट फीचर. वो भाई हमारा VGG16 वाज वेरी मच, वो तो था ही बढ़िया, ऑलरेडी प्री ट्रेन था. सो वी हैव ऑलरेडी एक्सट्रैक्टेड गुड फीचर एंड देन वी अप्लाइड मल्टी हेड. वन मल्टी हेड वी अप्लाइड जिसमें 8 हेड्स थे. यू कैन टेक 16 हेड्स ऑल्सो, आपकी इच्छा यार कितने लगाना है. ओके, तो डिफरेंट डिफरेंट हेड, डिफरेंट डिफरेंट, तो सम टोल्ड क्रॉस लगा दूं सर, सम वन टोल्ड एडिशन लगा दूं सर. ओके, सो मल्टी हेड कर दो यार भाई, सब सब ले लो तुम, और वहां से एक अच्छा सा आंसर ले लो, टेक अ गुड आंसर फ्रॉम दैट. ओके, so I did this thing only, and then there is nothing else left with me.
Sir, how about the second one combination, sir?
Which one?
The second one which you had.
Second one, sir. Like it's all, if you are applying multiple convolution and pooling and in between this thing, na multi-head, then also complexity is more, sir.
What are observations, sir?
Sir, that's what I told you, sir. I got good scores with the training, but the validation I'm not improving, sir. It's only
Second one,
50%. हाँ sir, it's
second.
like same only, sir. Not that much. I think
Okay, sir.
I think यहाँ पर तो शायद और भी इन दोनों में से कहीं और डिग्रेड हुआ. मतलब वो 50-50 से ज़्यादा हुआ ही नहीं. In one of the case, it increased. In one of the case, it was not improving at all. 50-50. Okay, so that's my observation. Or it's taking time. कई बार मेमोरी स्पिल हुआ ऑन माई कीगल ओनली. ओके, तो ये मेरा ऑब्जर्वेशन है. फाइन. एंड देन आई हैव अप्लाइड दिस गॉसियन. ओके, द गॉसियन नॉइज, दैट मीन्स एडिंग सम पार्ट ऑफ नॉइज इनटू द, बस यहाँ पर था खास काम, अटेंशन. ये आई डिड एक्सप्लेन यू एवरीथिंग. एंड देन आई एडेड गॉसियन नॉइज. ये बाकी आपको पता है, ग्लोबल एवरेज पूलिंग yesterday only explained. Okay, that means you are having a one value, average value of the entire spatial dimension, one average value. Dense neural network है. Batch normalization also explained. You need to normalize your data. The one which I told na yesterday, वो rich and poor वाला example, normalization. Again I added the noise. तो ये एक अच्छा सा architecture. This is one of the good architecture. You can follow this architecture. ओके, अब ज्यादा कुछ बचा नहीं है. VGG16 से वेट ले लिया, देन अटेंशन लगा दिया, एंड देन 4 to 5 layers I added from my side. That's it, done. 4 classes are there, तो मल्टी क्लासिफिकेशन है, एंड I trained my model, and you can see here the result which I got over brain tumor is 95% testing accuracy. You can see all are balanced, precision, recall, F1 score, support, everything is balanced like. Okay, so 95% score I'm getting with this algorithm, with this technique, by adding attention. Okay, I applied this VGG19 also, Visual Geometry Group 19. Okay, कुछ नहीं करा, आर्किटेक्चर पूरा सेम है. तभी I wrote 10 projects in my template. ऐसी दिखा दूंगा मैं आपको 10. Okay, again you can see I just took the same architecture and just I changed the model. Instead of VGG16 I use VGG19. ओके, पूरा सा वही है, पूरा सेम है. ठीक है, एंड देन यू कैन सी कि आप देखिएगा यहां आई गॉट 76% एक्यूरेसी. 19 पर डिप हो गया फॉर ब्रेन ट्यूमर इमेजेस. इट गॉट डिप इन VGG19 विद मल्टी हेड अटेंशन. जहां स्कोर्स आर नॉट कमिंग लाइक दैट मच रेलेवेंट. 16 तक तो ठीक था, क्योंकि विजुअल ज्योमेट्री ग्रुप जो है, इन विजुअल ज्योमेट्री ग्रुप VGG, ये 16 एंड 19 ये पूरा सीक्वेंस में है. ये इसका ड्रॉबैक है, दैट इज अ ड्रॉबैक, क्योंकि इमेज का साइज डाउन 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 कम होता रहता है. एंड यदि इफ यू डू डिक्रीज इन द साइज ऑफ द इमेज एट वन स्टेज ऑफ टाइम, आपको इमेज में कुछ बचेगा ही नहीं. यू आर नॉट गोइंग टू हैव एनीथिंग प्रेजेंट जिसको मैं आई कैन यूज इट फॉर द ट्रेनिंग पर्पस. इफ देयर इज नॉट अवेलेबल, अब फिर क्या कर लोगे आप. Okay, so I do have some concepts related to VGG19 also. Let me discuss that also. इसको भी मैं बता देता हूँ. सो वीजीजी विजुअल ज्योमेट्री ग्रुप है, ऑक्सफोर्ड यूनिवर्सिटी, दे डेवलप्ड 16 और 19 वर्जन्स हैं, 11 भी था. ओके, तो कई हैं इसके वर्जन्स. एंड ये आपका जो है एक आर्किटेक्चर जो कि कंपटीशन में फाइट तो करा था. आई टोल्ड इन द प्रीवियस क्लास आल्सो, इट टुक पार्टिसिपेशन इन द इमेजनेट दैट कंपटीशन. ये दिस आर्किटेक्चर हैवंट वॉन दैट कंपटीशन, गूगल नेट वॉन. ओके, गूगल नेट ने जीत लिया था, बट ये काफी चर्चा में आया. इट केम इनटू द हाईलाइट. 16. ओके, तो 16 में आपने यू हैव सीन द एंटायर आर्किटेक्चर, और उसी तरीके से 19 है. 16 तक तो वी हैव मेड. 3 और जोड़ दो उसमें, 3 लेयर्स, जस्ट ऐड मोर टू द 16, इट विल कन्वर्ट इनटू 19. ओके, तो वीजीजी में जो इनपुट होता है दैट इज आरजीबी, एंड दिस इज द स्टैंडर्ड साइज 224 224 224. भैया गलत लिख दिया, हाँ, 224 224. दिट इज द स्टैंडर्ड साइज यू गिव. ओके, फाइन. तो अब क्या है यहां पर? There are three fully connected which can vary from VGG11 to VGG19 according to the total number of convolution layer plus fully connected layer. In VGG11, 18 convolution are there, 3 fully connected. VGG16, 13 convolution are there, 3 fully connected. VGG19, 16 convolution are there and 3 fully connected. तो कुछ नहीं करना है, जैसा VGG है ना, वॉट VGG 16 है आपका. लेट मी शो यू दैट ऑल्सो. और 19 भी मैंने बना रखा है. ओके, लेट मी शो यू दैट. ये लोड हो जाए. दैट्स अ होम पेज ऑफ माय जुपिटर नोटबुक, सो लेट मी शो यू दैट. ओके, सो या हियर इट इज. ओके, जस्ट लोड द पेज. Okay, are you guys enjoying the session or not? Yes? Okay. So medical imaging 1. Alright, so this file will open and I will show you the architecture of VGG19. So that is 16 plus 3. 16 convolution and 3 neural network. Okay, fine. And here is the architecture. This is VGG19. Okay. So again, just like take from the 16. So this is first convolution block, 2 convolution, 1 pooling, 2 convolution, 1 pooling, 3 convolution, 1 pooling, 3 convolution, 1 pooling. This is additional 3 convolution, 1 pooling. In 16, till here we are having 4 blocks. I guess that's the thing. Okay, 16 हुआ कि नहीं हुआ? हाँ, देखते हैं. लेट्स काउंट. 16 में 1 2 3 4 5 6 7 8 9 10 11 12 13. सो ये क्या है? दिस इज योर VGG. ये क्या था? हाँ, ओके ओके ओके, 4 5. ये है आपका VGG 16. दिस इज VGG 16. And what I should do is just copy, Control C, and let me do Control V. ये लो, block number 6 लगा दिया. Okay, block number 6 I made. So यहाँ पर 3 more आ गया. Okay, so that will be VGG 19. We can see here in the document also. Okay, so that's what they are saying, 16 convolution and 3 fully connected. And 77512 is converted into 114096. See, like ये तो हुआ ही था 114096. 77512 to 114096 to 111000. कैसे आया ये? हाउ इट केम? सी देखो, यू डू स्टार्ट यहां से देखना. हाँ, you are having an image of size 224 2243, then 64 64 का कर्नल, तो ये हो गया. then 128 का kernel, so you are getting this thing. Then 256 का kernel, so you are getting this thing. Formula you very well know how you are going to get the output. The formula is 1 plus image ka height plus 2 into padding minus filter ka kernel ka height divided by striding. You know the formula, I have already taught. तो आप लगाओगे, you will get this thing. ओके, तो आपको ये मिलता चला जाएगा. देन 512, 512, देन 512, 512, 512, ये ऐसा इतना आ गया. ओके, सो हाउ मेनी लाइक we are having the convolutions here. Here you can see two cross convolution, 2, 4, 6, 9, 12, 1 pooling, 2 pooling, 3 pooling, 4 pooling. Okay, 1, 2, 3, 4, 5. Okay, 5 poolings are there. This is VGG 16. And then the network configuration और कुछ बता रहे हैं ऐसा ही है, बस the thing is you have to add more convolution to make it 16. बस ये हो जाएगा. ओके, सो ये क्या बोल रहा है यहाँ पे, VGG 16 contains 16 layer, VGG 19 contain 19 layer. That's it. वो दोनों में कोई अंतर नहीं है, 3 और लेयर, just add 3 more तो डन हो जाएगा. Okay, so this is VGG 19. Okay, and yes, I did with my code related to it. ये आपका पूरा आर्किटेक्चर है, मैंने 3 और पेस्ट कर दिया है यहाँ पर. So you are going to get the VGG 19. Okay, this is VGG 19, and then I used this thing only here in the brain tumor, and I got the result which is not as much as good related to VGG 16 as I got. Okay, fine. तो ठीक है, कोई बात नहीं, कोई इशू नहीं है. Okay, then I have used other algorithms like mobile net, inception net. Okay, my mobile net, inception net, I will let you know. Today I made one more project, that is diabetic retinopathy. Okay, and in diabetic retinopathy, I'm having the images of this retina. One is having diabetes, one is not having diabetes. Diabetes, that's what I am having, and colored images. I hope if you have seen, तो आपको you will get it. Okay, yes, ma'am. Yes, any doubt, please let me know. Okay, अब the approach which I do follow ना in each and every code, that is all same, ताकि मैंने simplify कर दिया. This is the base path where images are present. These are the categories. I converted data frame, DA बना लिया. I already taught this thing. Then head print करा, tail print करा, then shape I printed, column printed, duplicate printed, null printed, information printed, number of unique, then number of counts in the categories, DR, no DR. Then I made count plot, and then I made the pipe. Everything, the entire approach for every project is same. मुझे टाइम नहीं लगता प्रोजेक्ट बनाने में, पहले ऑलरेडी आई मुझे पूरा फ्लो पता है व्हाट टू डू. तो दिस आई डिड. Then I displayed 5 images. Here you can see diabetic retinopathy. This is DR images, and these are no DR images. No diabetic retinopathy. This is diabetic retinopathy. I'm having colored images already, तो कोई issue नहीं है. Okay, fine. And then I perform same code, label encoder. That means I will encode the labels. Then I do perform the sampling of my data to make equal both of them. However, they are already equal. Okay, nearly equal. This is 49 and this is 50%. So they are nearly equal. Okay, and then next is 1050, both become equal. All right, and then I imported all these TensorFlow and libraries. I divided my data into training, testing, and then I performed the pre-processing, in which I took 3 channel. Size of the images should be converted to 2 to 4. 2 to 4, that's what the expectation of the pre-trained models are. Okay, so same code I have just used in brain tumor also, exactly same, no changes at all. Okay, Just only the thing is I changed the class mode to be binary. In brain tumor I was having four classes, so that is sparse. The class mode will be sparse if you are having multi classification more than two, but if you are having only two classes, class mode will be binary. Okay, so here I did a change, that is a simple change, binary. Rest all is same. Okay, then I use the GPU, then I imported VG16. If you want to verify, see, this is my this is my architecture for brain tumor. This is my brain tumor architecture. Let me copy this entire architecture and put it here on diabetic retinopathy. You will see the same, entire same architecture. Just only the thing is, as I am having binary classification, so I change the activation function to sigmoid. If you are having two classes, change the activation to function to sigmoid and take only one neuron at the final layer. Take only one neuron at the final layer for binary classification. But if you are having multi classification, you have to take the number of classes at the final layer. That is four, because I was having four classes and the activation function was softmax. Here is a bit change, and also there is a change here in compilation. In multi classification, I do take sparse categorical cross entropy. In binary classification, I take binary cross entropy. Okay, these are few changes which I did. I kept the entire architecture same. Everything is same. And then I trained my model. You can see the result. Okay, one more thing I added. Uh, Before training, what was the time? After training ends, what was the time? Just I need to check how much my algorithm takes. What is the computational time my algorithm take on over the resources which I'm using? It took only 58.6059 seconds, nearly 2 seconds less than a minute, to train my model over the data, over 1000 images. If it would be like 10,000, then the time may vary. It will be for 10,000, the time may vary. Okay, but for 1000 plus images, it took only 58 seconds to get trained over 5 iteration. And the result which I got here is, here you can see the result, 92% accuracy of detection. Okay, accuracy is 92%. Fine. I am coming across. Yeah, yes, sir, ask the question.
So then once we have trained the model and done the testing and validation, and we want to go towards prediction with novel images for diagnostics, do you cover that in this code, or can you
Sir, once I
explain how we
train
can
my
do that?
model,
And also,
yes.
is that Ms. Mirza has.
Okay. After training, what you are expecting, sir? Yes.
For prediction and diagnostics, if we have a new image that the model's never seen, and we want it to classify it as one of the four categories, or in retinopathy as diabetic or not, we want to take a new image and run it through. How do we do that?
Sir, we are taking the testing data that is unseen for a model. That's the first thing over which only I am finding the confusion matrix and the classification report. This what you have seen, what you are seeing. You can see CNN model dot predict over test data. Test data is something which the model haven't seen. Model is trained over trained data and has been validated over validation data.
I'm talking about individual
Individual, yes,
images
sir.
from.
We will see that thing also. That means we can pick any of an image from any like different data set. Okay, and then we can use the same model for the prediction. Only the thing is what we have to do, whatever be the pre-processing we have applied so far, we have to apply the same pre-processing over that image also. Okay, for example, if you are saying, sir, one image, take one image and do perform the prediction over it. That's what you are saying. Whether it is whether it is DT or no DT. That's what you are saying. Just have
Yeah,
a try.
I'm looking towards a diagnostic. Somebody comes into an office, you get a scan. They want to know whether or not they
Whether or
have a
not,
brain tumor.
sir. That
So
means
you
you.
run that image through, and the model says yes, it's classified as a glioma.
That means you can upload an image and just your
Yep.
model should predict whether it is DT or no DT. Okay, fine. Once you upload an image, you have to perform the pre-processing of an image. Okay, that I will
Yep.
be including in my further course. I will take one of the project in which I just add 2 to 3 lines of code. You need to perform the pre-processing. That means convert that image into 224. It should be in RGB because we can't directly perform the prediction over a random image. No, unless and until your pre-processing is not complete, you can't do that. Okay, so first we have to do this thing. Okay, and after performing this thing, then we can give anything else. Did I did on the pre-processing? No. Then this conversion you can give it to the model for prediction. Okay, maybe some
Understood.
like numpy array, you have to convert this image into an array. Maybe like this could be one of the thing. I will check it out. Okay, and you have to give directly to the prediction. I will include this thing. I'll pick one of the
Okay,
image and do
cool.
the prediction, sir. Yeah.
And I think that there's a related question in the messages
Yeah.
from Miss Marza.
Okay. So actually, I have it included at particular time because I'm already predicting. I'm already testing my model over the test data. So test data is unseen to the model, and this is what I result got 95% accuracy. Okay, for the brain tumor, and this is for diabetic. I've got 92% over the same. Sir, the concern part is okay. We can test over a single image also. The concern part is, sir, you can see how commonly I'm using the architectures and how I'm getting the results. Sir, that could be one of the questions, sir. That how a common architecture is giving good results on different data. Am I correct or not, sir? Am I correct or not? Yes, that's my question. You are using diabetic retinopathy images, you are using brain tumor images, you are using breast cancer images, you are using different disease images, and you are using such kind of architecture. How it is possible that it is giving 90% plus scores on different problems? What made your model to do this thing? Okay. Well, I believe that in my architecture, obviously, multi-head attention has helped. Gaussian, Gaussian also helped because I added noise into my data. So to have a variation, it added a variation in the input, and because of the variation, obviously, I got some more diversification in my data. So this thing also helped, and this thing also helped. Okay, I applied batch normalization to prevent the overfitting. I can apply dropout to prevent the overfitting. So these are the normal layers. But multi-head and Gaussian is something you are trying to focus, attend on the relevant features, and you are trying to add the diversity in the data. This helped me a lot to get the good scores. Even I'm having so many problem statements, but my okay. And in diabetic retinopathy, I have used one more architecture that is mobile net V2. It's a small architecture. Okay. And this small architecture, its name is a small architecture. Again, sir, let me tell you one thing. Everyone, I is just a copy paste of above code, nothing else. It's just copy this code of VGG16, paste it down. Okay, and just instead of VGG16 or VGG19, change to MobileNet. Just change to MobileNet. That's it. Nothing, no additional efforts I did. And over the same architecture, I again took the starting time and the training time for the training, and I got it as 40 only 40, in 43 seconds. My model got trained. Previously was 58. Now it is 43. Okay, so 5 iterations, only 43 seconds, and you can see the scores. I am increased by 2% more. In VGG16 it is 92. MobileNet it is 94% accuracy over testing data. Okay, so the architectures like VGG16, okay, VGG16, VGG19, Inception, Exception, MobileNet. These are for me, for my case, whether I have been working on any of the problem statement of the medical, all these algorithms have proved to be the best for me. Everywhere I got good percentage of accuracy with attention mechanism and including the Gaussian noise. Same configuration if you use, you can achieve the same. Okay, fine. Yeah, please say. Yes, ma'am.
Sir, can you hear me?
Yes, yes.
Actually, I had the same question as doctor before, that can we train, like, because these are medical images, can we just like train the model with an outside, I mean, test the model with an outside data image?
Yes, you can do that.
So as you said, yes, we can do,
Uh-huh.
but as you said that testing of the, I mean, the model itself with the subset of the data set which is already available within the model itself, I mean the whole data set, this is what we are doing, right? So
See,
in literature also, I think they are always testing with the
uh-huh.
subset of the same data set, right?
Subset of the same data, but that data
Like
is
you're
not used.
dividing, like you're dividing,
Huh, huh,
like
huh,
you're dividing it into
huh,
data,
huh.
training data and testing
Testing
data in the
data.
beginning only.
In the beginning.
But when you do this, like when you run this code multiple times, doesn't the model get acquainted with the
No,
same
madam.
data? That means it's every time seeing this test data also, right?
No, ma'am. No, ma'am. Not every time if I run the model. See, there is one part mentioned here in the code. If you see in a random state 42, there is one thing.
Mm-hmm.
Your concern is valid. So, ma'am, when I divide my
My
data,
concern is,
uh-huh,
if I can tell you in lame language, my concern is this model is like my child.
uh-huh,
She is trying to learn from these
uh,
textbooks,
huh,
and she can mug up and she can learn and iterate, or she can remember the stuff. But when I keep her on a job, I
hmm,
mean, when I take her in an external environment,
hmm,
like an external image,
hmm,
I want to see how is she performing there on her job roles, for example.
okay, okay, fine.
So,
So, ma'am, here it
do
is
you
the
get
random
me?
state
So
for. Yeah, yeah,
that
got it.
that was just one
So, ma'am, this is
question.
the random state 42, madam. And
Okay.
the division of data, if we do take random state 42, it will, madam, remains the same. It doesn't mean that when you r- again run the code multiple time, okay, madam, but this is the thing which keeps the fraction of the data which we took previously for the training, then testing, then the validation, that will be the same kind of distribution because of this random state 42. Okay, so in data splitting also that can be used, and ahead also that can be used. Okay, in machine learning we do use random state. So for example, if I run the entire code multiple times, the score or the accuracy which I achieved in model training, that will remain same. For example, one time I ran the code, I got 85% accuracy. Second time, if I run the code with random, when I put random state 42, still the accuracy is 80% only. It will not change, madam, because of this parameters, these hyperparameters. They will help us, madam, for that. So your
Okay.
test data is not seen by the model. You gave
So
training
every
data and
iteration it will,
validation data.
okay. So
That
every
is simple.
iteration it will see a new image, you mean, from the test data itself.
From that will be considered as a text new image, it will see.
So, but we can also, like,
Huh,
suppose I'm a radiologist and
huh,
I'm not
huh,
able to like see it from my own eyes. So
hmm,
I can use this machine learning,
huh.
I mean, algorithm,
Yes,
and
madam.
put my patient data into this,
Yes,
right?
ma'am. Yes,
So
ma'am.
that would
Absolutely.
be an, always it would be an external data.
Yes, ma'am. That will be external data, and for that purpose only, we are training our model that it should detect properly. So, ma'am,
Yeah.
here.
So we can, like, external image, we can like add it, right? So
Mm-hmm.
that option we will always have.
Yes, ma'am. The option we are always have, and I will be adding an external data to it. But the image
Yeah.
which you are going
That's
to add, for
wonderful.
example, this is the test image. Okay, DR and no DR. This is the test image. Your
Okay.
image should be like in, if it should be like this. You upload this
Yes. Yes.
image.
Of course.
Okay, like this one only. We have to convert it into 224
Yes.
RGB, and then we have to convert it into like specific dimension which is required for the model, and then directly give to the prediction. It will do.
Yeah,
It will,
I
nothing
get it.
else.
Like the pre-processing which we have done
Hmm,
for the
hmm,
training part, it
hmm.
should be same
No, same.
for
That needs
here
to be done.
also, so that the image matches the channels and all.
Yes, ma'am. That should match.
Okay, okay. Thank you, sir. If you can add that one, it would be like
Yes, ma'am.
more
Yes, ma'am.
engaging for us.
Sure, sure, ma'am. Tomorrow I will, because I will be showing more projects now. So tomorrow I will add that part also.
Yeah,
Okay, ma'am.
thank you so much.
Okay, okay. Yes, sir. Thank you, madam. Yeah.
Thank you. I had a question about the multi-head attention, and I
Huh.
was wondering if it might be more beneficial to use multi-head attention architecture when dealing with time series or video or
Yes, sir.
text, simply
Yes, sir.
because of
Everywhere it's
the way it
applicable.
handles long-range dependencies?
Yes, sir. It's everywhere applicable. In fact, just recently I have shared one code in which I have used multi-head attention with traditional machine learning algorithm. I've shared one code where I've used multi-head with random forest and XGBoost. Okay, sir. And that was so optimized, the XGBoost was so optimized that it is taking less time to perform with the same accuracy. 100% accuracy over a data with less processing time with multi-head attention,
I guess
with attention
I guess
mechanism.
my question is really whether or not it's better suited for time series data rather than a single static
Sir,
image.
so time series also, like we are taking it as a sequential data because text is also sequential. Time series is also
Yes.
sequential data. So, sir, multi-head is already successful in sequential data, no, sir. So, time series is also
Yes.
sequential, sir. Obviously, we believe that it will be successful there also. Okay, sir. So, I think I'm looking forward for more codes related to it for sequential data also. Okay, fine. So, yeah, that's the multi-head attention VGG16, VGG19. Okay, we have set up all this discussion. I am having uh, one more architecture to have. Let me have some a basic discussion over this architecture, Inception V3 model architecture, because that's what I need to cover. Inception also and exception also I need to cover with the multi-head. Okay, since I already talked about the drawback of VGG 16 and the 19, that is, it is sequential in nature. So, in order to break that particular chain or sequence, we are having Inception V3 architecture. Okay, and Inception V3 again, it's a deep learning convolution neural network based architecture, and we are having Inception V1, we are having Inception V2, we are V3, V4, we are having such architectures, and such kind of architecture was introduced in 2014 with Google Net, and this architecture won the competition, no, sir, for ImageNet for classification. Okay, so Inception V1, when multiple deep learning layers of convolution are used in the model, it results into overfitting of the data. That's what happened with VGG. Multiple layers, C, all these are just used like this now. It will result into overfitting of the model. Okay, so to avoid this issue, Inception V1 models are used with an idea of using multiple filters of different sizes on the same level. That means don't put it like in this particular sequence. Keep the data on keep the filters on the same level. Okay, it will be like parallel. Just we should be having some parallel connection of the layers. I'll show you the architecture. Okay, so the inception model is made up of multiple inception modules. It comprises of parallel layers 1 cross 1, 3 cross 3, 5 cross 5, and 3 cross 3 pooling, max pooling. So these are in parallel rather than in a sequence. Okay, convolution, we very well know. Feature extraction, pooling, we very well know. Dimensionality reduction. And the different sizes of convolution will be used here in parallel and they will capture different, uh, different sizes of information from the picture. Okay, this is how we are going to use. From the previous layer, whatever we are getting, we are submitting it to parallel convolutions 1 cross 1, 3 cross 3, 5 cross 5, 3 cross 3 pooling. And then we are going to concatenate the results which we are getting from them. That's what we are doing. So arrange all these things in parallel and then give it to the filter for concatenation. Okay, got it. So this module of Inception V1 is a naive form. Okay, one of the drawback of naive form is that even 5 cross 5 convolution is computationally expensive, time consuming, and requires high computational power. Okay, because we are having 5 cross 5, this convolution. See, I already told. We use 3 cross 3. In VGG16, 3 cross 3 filter were used. But if we increase the number of filters, size of the filter, 5 cross 5, 7 cross, this is not preferred. This is rare. So here in Inception V1, 5 cross 5 were used. Computationally expensive. So to overcome the authors of the research, they added 1 cross 1 convolution layer before each convolution. Okay, and they have given new architecture. That means from the previous layer, now 1 cross 1, 1 cross 1, 1 cross 1. Give this to 3 cross 3, then give this to 5 cross 5, but before that use 1 cross 1. Then give to 5 cross 5. Then again 1 cross 1, 1 cross 1, then all the results are concatenated. Now the ideology has been changed. Because of overfitting, we are changing the ideology. Okay, fine. So I think that makes a sense for today's session. Okay. So did you enjoy the session for today? Did you
Yes,
understood
sir.
the class? Okay, let me stop presenting. Let me stop recording also.